All right. Sorry? Okay, here we go. Okay, so continuing on with our likelihood stuff. So I talked about how to take the likelihood and convert it into a cost function. So someone came up to me during the break. The reason why you convert the powers into sums with the log is because it allows the computation to be a little more palatable in floating point math. Because if you have a bunch of numbers that are less than 1, if you take the product of them, you have like 100 or 1,000, then the number is going to be actually pretty small, and it'll give you a lot of imprecision. So what people usually do is they take the log of each product and sum them all together. That way each number will be greater than 1, so that when you sum everything up, you get a number that's a little more palatable to deal with that, and it makes minimizing this a lot easier. So there's 2 reasons why you want to take the log. Okay, so how do we actually minimize the cost function? So we talked about gradient descent. If you recall from the algorithm, what you do is you have to start off at some initial point, right? So you have to initialize theta 0, theta 1 up to theta n to be whatever you want. And in this case, well, you can assume that they're all 0 for now. And then you repeat the following until, a maximum number of iterations, or if the algorithm converges, if the difference between the costs is less than some amount. So you have theta j updates to theta j subtract, and then alpha, which is the learning rate, and then this should be theta j, right? It's the derivative or the gradient in the direction of where the parameter goes for theta j, and you have to simultaneously update. Okay, so we can figure out how to minimize or get the best parameters or maximize the likelihood or minimize the negative log likelihood given this algorithm. Okay, so the question that we have to deal with is how do we find, the partial? How do we find this? Okay. So if you recall, this was our cost function from before. 1 over m, and then this is minus. Okay, and then subtract. Remember, there was a negative on the outside because this became a cost function. So I just took the negative and I just factored it in for every term on the inside. So that's why this is a minus now. And then log 1 minus. Sorry, I can't write today. So this is theta. And whatever. Okay? That's good. So we're going to assume m is equal to 1. So the reason why we do this is because it'll make the math a little easier. So let's just assume m is equal to 1, find what the gradient is, and then if you want to generalize this to m training examples, you just have to take that term that we find and just sum over m examples, because derivative is a linear operation. So if you find the derivative of a bunch of sums, it's the same thing as just taking the derivative of each and just summing everything together. Okay, so assume m is equal to 1 and find the gradients. Okay, and then for m examples, sum all together. Okay. Okay, so in this case we have, it just gets simplified to minus. Okay? And then minus. This is just, we're doing it for 1 because it'll make the math a little easier to deal with, all right? Okay, so there's just one training example for now. Okay, so we're dealing with that. Just move now. Actually, let me get my mouse. It's make it a little easier to scroll. See if I can find it. Okay, because I hate using the pen to scroll. It doesn't. Resolution is pretty bad, so okay, that's good. All right. Okay, let's see here. All right. So, whoopsie. So let's just make a little bit of a side note. Okay, because we have to take the derivative of this, okay, we're going to have to take the derivative of the sigmoid function because that's what the hypothesis is. So if you recall aside, let's see here. So this is the sigmoid function. All right? Because we have to take the derivative of this guy over here, inevitably you're going to have to take the derivative of a sigmoid term because that's what the hypothesis is. So this is also equal to 1 plus e to the minus z to the power minus 1, right? Because it's just, to the minus 1 is simply the inverse, or simply 1 over. Okay? If I want to take the derivative of this guy, okay, what do? It's the power rule. So you bring the minus 1 to the front, okay? You write out what the term is, and then you subtract to the power of 1, so minus 1 becomes minus 2, and then you take the derivative of the inside. It's the chain rule, right? So if the derivative of this is 0, and then this is just minus e to the minus z, and then these positives, this becomes positive because you have the two minuses here that cancel. So finally we get, this is 1 plus e to the minus z all squared. Okay? One of the best tricks you can do in mathematics is to either add 0 or multiply by with 1. So what I'm going to do here is I'm simply going to add and subtract by 1. I'm not violating any mathematical laws. This is essentially equal to the same thing. I just have a 1 on the one side and a minus 1 on the other side. The reason why I'm doing this is it'll make it a little easier to, represent this function. So in this case, I can split this up into two fractions. Okay, so there's 1, and then here's another 1. Okay, and then if you take a look, this is essentially to the power 1. So I can take one of these guys and cancel with one of those, right? So this becomes 1 plus. Okay, so now if you take a look here, there's a common factor of 1 over 1 plus e to the minus z that I can factor out. And this becomes 1 plus e to the minus z, and then this becomes 1 minus. Okay, now if you take a look, this here and this here are both equal to what? G of z, right? So in that case, the derivative is equal to the original function multiplied by 1 minus the original function. Okay? So I can actually represent the derivative of this in terms of itself. So you take the sigmoid function by itself and you multiply by 1 minus the sigmoid. So that's an important observation because when I find the derivative of the cost function, it'll make, using this will make it a little easier to deal with. Okay? So that's how you can represent it. That's good. All right. So just a couple of other properties we're going to take a look at before we continue. So recall, okay, if you take the log of a function, okay, let's call this, I guess, y. Okay, if I took the derivative, okay, if you remember, you take the, so if I had just y is equal to log of x, okay, if I took the derivative of this, it's just 1 over x, right? So it's one of those special derivatives where it's just 1 over x. This is log to the base, log to the base e. So if I have a function in the inside, this is equivalent to 1 over f, right? And then the chain rule. So this is equal to f prime x over f. Okay, so let me just move this over this way. Okay, so there's one. And then finally, let's say I had a composition of functions. So let's say I had f of g of x. Okay, so this is the same thing. So if I wanted to find the derivative, this is 1 over f of g of x. Okay, and then I have to take the derivative. And then this is again chain rule, so you get g prime x. Okay? I'm doing this because it'll make doing this cost function stuff a lot easier. So there's two things you have to remember. This guy here, all right, and this guy here. So those are the two things you got to remember in order for us to proceed. Let me just move up. Sorry. Here we go. All right. So we had this. Let me just get this guy from before so I can proceed. Just copy. Okay, so this is what I had from before. Okay, so now what I got to do is, okay, so when I take the derivative, I have two terms to deal with. I have this guy here and this guy here. Okay, so if I took the, let's see, if I took the derivative of this guy, okay, actually no, let me just, one moment. So recall the hypothesis was equal to the sigmoid, okay? Okay, and This is equal to theta 0 plus theta 1 x1 and so on. All right? And then g was the sigmoid from before. Okay. So this is what I have. So what I need to do now is I need to find, so when I find the derivative of this, it's the derivative of the first term with the derivative of the second term. So let me do both of them separately and we'll combine it all together. So well, I want to find the derivative of this guy. Okay. Okay. What was it? It was basically 1 over, and then each of theta. I'm just going to replace this with g. Okay. And then I got to multiply this by the derivative of this guy, which is what? G. Right? And then bracket 1 minus. This is just chain rule. Okay. And then you have to multiply this by the derivative of the inside. And if you take a look, I'm doing this with respect to theta. So this is with respect to theta j, because that's what I have to find the derivative with respect to, right? So if I'm doing this with respect to theta j, what happens? So let's see here. So I have this term here, and then when I take the derivative, everything cancels except for the theta j term, right? So when I differentiate that, that constant goes away. So what I'm left with is just x of j. Okay? So that's what I have here. But then if you take a look, this guy cancels with this guy. So what I'm left with, so oh, sorry. This is equal to, let me see if I got that right. Yep. So this is 1 minus, in this case, this is just, I'm just going to represent it as is for now. Same thing. Okay? So let's this guy over here. Okay. Let's do the next one. So let me just do d by theta j here just to be sure we're unambiguous. Okay, so same thing as before. So 1 over 1 minus. Okay, and then we multiply this by the, let's see, your derivative of the inside. In this case, let me see, just double checking, 1 over, right. So in this case, when you differentiate on the inside, the 1 goes away, and then there's still a minus. You have minus, and then derivative of this is g, and then 1 minus g. Okay, and then multiply this again by the derivative of the inside. In this case, it's still x of j. Okay, and then what's going to happen is this guy cancels with this guy, and you're left with this. Let's see. All right. So yeah, this is all very fast. No, just remember what the final result is at the end, and you'll actually be pleasantly surprised. Okay. Remember, xj is the jth feature of the x point, so there are n features with the bias term, so theta j is the jth parameter. So therefore, okay, we have the minus y, and then, okay, this is the term from before. Okay, so this is the first term. Let me just, you know what, let me move this down so you can actually see. Oops. Yeah, here is a, okay. So you've got that, okay? And then when you differentiate, remember this is with respect to theta j, so the y stay constant, so this is this term here, and then minus 1 minus y, and then this is this term here. Okay, so if you actually expand this out, this is minus y xj plus h theta x y xj, okay? And then when we expand this, minus minus becomes a plus, so this is plus xj minus minus, so this is, okay, so if you take a look here, so I have minus, sorry, come on, so minus. Okay, and the negative becomes a plus, and then you subtract it again. That becomes a negative as well. Okay? So this guy and this guy cancel, and then we're left with a very familiar term. So actually, let me see here. Did I get, sorry, this is a positive. Because you have the minus and the minus that cancel. Sorry about that. So finally, that looks a little familiar, I think. So therefore, right, and then for m examples, right, you want to average it. So you don't have to average it, but for m examples, it's 1 over m. Sorry. Okay. That looks a little familiar. If you remember from linear regression, that's exactly the same hypothesis. It's a little kind of cool how it works out like that. So if you want to find the gradient for logistic regression, it's exactly the same way that you'd find it with linear. But the only difference is that the hypothesis is different. So with linear regression, it's a sum of weighted numbers. But the only difference between this and logistic is you find the sum of weighted numbers and then you also apply the logistic function to it. So there's only one extra step you need to do in order to find the gradient, and that is to apply the logistic function to your weighted sum. So this actually looks like, it's pretty much the same as linear regression almost. Okay, so it looks identical to linear regression. So yeah, if you don't want to remember how this is derived, just remember the final result. It's basically just the same as linear regression. Okay, so caution. Not the same. Algorithm. It looks the same though, but the point of linear regression is to predict outcomes. It's to predict continuous valued outcomes. With logistic regression, you're predicting the class that belongs to certain classes, and you're trying to figure out the probability of whether that output belongs to a certain class. Okay, it's not the same algorithm because the hypothesis here is nonlinear. It's a sigmoid function, right? In logistic regression. Okay, and h of theta is linear in linear regression. All right, so it's not the same algorithm, but it cosmetically looks the same. So this is what the final gradient descent looks like. Okay, therefore, let me just move up so you guys can copy. Okay. All right. So let's see here. So the first part, initialize theta 0, theta 1, up to theta n. Okay. And then finally, repeat until convergence. Okay. So minus, let's see here, 1 over m, and there's an alpha 2. Take notice that, remember in linear regression there was a 1 over 2n factor in the cost function, and that's not seen here. So 1 over m, summation from 1 to m. Okay. And that's it. So, and there we go. And then remember, okay, the hypothesis here is the sigmoid function, okay? It's not the, sum of weights. It's still the sum of weights, but you're applying an additional operation to it, okay? So you have this, and the cost function was this. So there's two different cost functions now. Okay? All right. So there's 1, and then there's 2. So remember, let's see here. So this was, sorry, let me just add this all up together. Sorry, so this is, okay, and then this is y of I, and I. Okay. So the algorithm itself is fine, but when you want to actually evaluate the cost function is different. It's not the sum of squares anymore, it's the log likelihood. So those are the two differences. One, using logistic function, and 2, the cost function changes. But the algorithm itself with gradient descent is exactly the same. You just got to remember to post-process the weighted sum with the logistic function when you're done. Okay? Okay. So let me just do a quick divergence here and talk about one of the discussion questions in your lab, just to throw you a little bit of a bone. So aside. So we've dealt with regression and classification so far. So one question that you're probably asking is, can we use linear regression to perform classification? Is that possible? The short answer is yes, but it does a pretty crap job at it, and I'll tell you why. All right? So aside. Can we use linear regression for classification? Yes, but poor performance. So why would it be poor? Why don't we just use linear regression for everything? Well, I'll tell you why. If you remember the goal of regression is to find the best fit line that fits through as many points as possible, right? And classification is to figure out whether or not an input belongs to a certain number, it belongs to a certain class, given a certain number of classes. Okay, so regression. So find the best line of fit. Sorry. Through as many points possible. Okay, and classification, as we talked about, classification is to find the, well, if you take all your points and then you're plotting them on on a grid or something, the point of classification is not to find the best line that fits through all the points. The point is to find what's known as a decision boundary. It's the line that best separates between the two classes. So that's why it's different. One, you're not finding a line through as many points as possible. You're finding that line that best splits between one class and another. That's what's known as finding a decision boundary. So on one side, it's a positive class, and the other side, it's a negative class. That's the point of classification. All right? So I'll find the line that best separates the classes. All right? This is what's known as a decision boundary. And we'll talk about that more in a little bit. But I just wanted to, talk about regression here and why it's bad in classification. Okay, so for example, let's say we have, suppose we have the following data on tumor sizes. And whether or not it's benign or malignant. So let's say we have this, and we find the prediction model. So let's say I had something like this. So this is 0 and this is 1. So this is benign and malignant. This is benign. Let's say I had a bunch of points here. This is the nose side, and this is tumor size. Usually when you have larger tumors, it's classified as malignant. So something like this, I guess, for example. I don't know, something like that. I guess, something like this, okay? And if you were to fit a line through regression, what's gonna happen is that it would look something like this. Actually, no, sorry, this is bad. Okay, so this is linear regression. Okay? And then I guess with linear regression, what you can do is you can take a look at, if it's greater than, you can threshold, right? If this is 0.5, right? Then I guess you can say that the decision boundary is over here. Or not decision boundary, but here. Here's the cutoff. Whatever this point is, okay? So this is the cutoff point. So any point that is less than this point you can consider as benign. Anything greater than this point you consider as malignant. Okay, so this is what the linear regression will give you. But let's say you added a new point to your data set. Let's say the point was way out here somewhere. Okay, so this is a new point. Now, if you're doing this with regression, the point is to fit a line through as many points as possible. So if you decide to run through and perform linear regression again, what's going to happen is that this line is going to shift. It's going to move over, probably over this way somewhere, because it has to fit through as many points as possible. So if you wanted to do classification, right, you want to find the best cutoff where the point is going to happen. So in classification, it would probably be over here somewhere instead, right? This is what classification does. So if you put a new point that's way, way, way out there, classification will not change where the cutoff will be. So even if it has an outlier that's way, way, way past over here, the decision boundary stays the same. This is past that cutoff. But if you do this with linear regression, what's going to happen is that that line is going to skew because it wants to fit as many points as possible through that best line of fit. So if you have an outlier, that line is going to change, which means that the cutoff will change, and that will probably introduce more misclassifications. So that's why linear regression is bad, because if you have a bunch of points that are extreme, then that line is going to change, and you'll probably get less accuracy because that line will change. All right, so let me see here. More data. Let me see. How would I phrase this? So adding one more example that is extreme. Oops, will skew the line of best fit. Okay, so and that means more data will be misclassified. Or it can be misclassified. Okay, and with classification is unaffected. Okay, so that's why you don't want to use linear. You can if you want, but it's bad because as soon as you introduce a point that is really, really extreme, and then if you try to train your model and get the parameters again, it's probably not going to do any good. You want to consider that extreme point to be part of that positive class, and you don't want to skew any of the other points that were successfully classified from before. Okay. That make sense? Okay, good. All right, so let's go on to decision boundaries. Here we're going to take a look at some nice pictures. Decision boundaries. So what I was talking about that. What decision boundaries are if you imagine all of your points, all of your training examples, and you plot them onto a nice grid, right? Each feature is a dimension. What a decision boundary does is that it's the best line or the best plane or whatever dimension you're in, it's the best way to separate between the two classes. That's what a decision boundary is. Okay, so a decision boundary is the best line of separation between two classes. Or not two classes, between classes. Remember, we're only dealing with two class for now, and we're going to talk about multiple class later. So if you remember from logistic regression, the logistic function or the sigmoid function, there's a pretty special property. So we have h of theta. If this is greater than 0.5, you classify it as a positive class, right? And if it's less than 0.5, then it's a negative class. Oh yeah, another student provided a very important point during the break. It's sometimes what people do is that they don't allow the system to give you positive or negative class. What they do is instead is they just output what the probability is, because you know h of theta is the probability that it belongs to the positive class. So what people usually do is that instead of saying that it's positive or negative, just output what the probability would be. So if, let's say the probability is 0.8 or 0.9, and then you let the user decide whether or not it's positive or negative. It's what's known as a decision support system, where the system only helps you make a decision, but it actually doesn't make the final decision in the end. that'll be up to you. So it's what's known as a decision support system. So it doesn't give you whether or not it's positive or negative. It just says, hey, there's an 80% chance that this belongs to the positive class, and I'll leave it up to you to decide. Okay, so you can either say it's a positive or negative, or you can say, hey, this is the probability, and you decide for yourself. So there's one of two ways you can approach this. All right? Okay, but in this case, we'll just go ahead and make it positive or negative. All right? So if you remember, it was this function here. Okay? And then remember that if the input was 0, then it's equal to 0. Sorry, not 0.5. Yes, sorry. This is good. Here, this is important too. So if the input is 0, then the output is 0.5, and that's right at the threshold where the boundary is going to happen. Okay? So let's see here, h theta x. So in this case, between here and here, it's safe to say that if the input is 0, then the output is 0.5. Okay? And then finally, we can make another statement. So therefore, when this term, the input into the sigmoid, is greater than equal to 0, then you predict positive, right? And then when it's less than 0, you predict negative. Right, because when the input to the sigmoid is 0, that's when it's 0.5, and this is where the boundary is. This is where the boundary is. Okay, then this is another thing that we can say, is this thing here, the sum of, the sum of squared terms that we're dealing with, if that whole weighted sum is bigger than or equal to 0, then it's positive, and if it's less than, this is negative. Okay, so this term here, this theta transpose, okay? This is what's known as the decision boundary. This here is the decision boundary. So this is the fine point, or this is the last line of defense, so to speak, where when you evaluate this function, you check to see whether or not it's, it's positive or negative, if it's bigger than or less than 0. And then depending on what the sign is, then you predict if it's positive or negative. So this is what is known as a decision boundary, and this is also what is known as a linear discriminant function. Because it's a linear function here, and then discriminant because it allows you to choose between whether or not it's a positive or spam or negative non-spam. There's a discriminant between two classes. It's what's also known as a linear discriminant function. And we'll talk about that later. It'll be in the next class. Okay? So, decision boundaries determine the region of space that instances are classified into. Okay? So if we take our training examples and if we plot them on some grid, some grid that makes sense to us. Plot them on some grid, whether it be Cartesian or polar or whatever, some grid. The decision boundary splits between the two classes, right? So the decision boundary splits the space. Okay, so on one side of the space, that's where the positives would be, and on the other side of the space, that's where the negatives are going to be. So one side is for positives, okay, and the other side is for negatives. Okay, and then what you do here is if you want to figure out whether or not a input belongs to one class or another, all you got to do is just take a look at the decision boundary and figure out which side of the space is on. If it's on one side, then it's going to be a positive class, and if it's on the other side, it's going to be a negative class. So that's the purpose of a decision boundary. It actually allows you to figure out which class you want to make the point belong to, and you just have to observe which side of the space it belongs to. Okay, so with new instances, check which side of the decision boundary it falls into. Okay, and then choose the class where that point falls into. That's the prediction. Okay, that's pretty cool. All right. Okay. All right. So here's a quick example. Okay, I'm only going to do it in 2 dimensions because if you go to higher dimensions, you can't really visualize it. And when you go to n dimensions, the best line of separation is what's known as a hyperplane. It's what's known as an n-dimensional hyperplane. So in this case, when you're dealing with 2D, then the hyperplane is a line. If it's in 3D, then the hyperplane is a plane. So when you get to n dimensions, you can't really visualize it anymore. So people, what they call as the line of separation is what's known as an n-dimensional hyperplane. All right. So example. Suppose we had 2D data, and we found the parameters. Let me see here. Just double check. Just talking about perceptron 1, 2, 3. Okay, and found. I'll end with the perceptron one. Found the parameters. So let's say, we had these parameters here. Okay, and then let's say I had a bunch of data like this. For example, okay, this is the negative class here, and then I had a bunch of, let's say this. You're not going to really see it separated nice like this in practice, but it's okay. Okay, so the decision boundary, this is x1, this is x2. Okay. So this is minus 1 plus 2x1 plus 2x2. And let me just isolate this so that the x2 is on one side, and the let's see here, 2, 2, 2. That's fine. And then the x1 is on the other. So in this case, we have 2x2 equals, and then this is 1, and then let's just divide. Okay, so this is what the decision boundary would be. So in this case, I have an intercept. Let's say the half was over here, okay, and 1 was here, and then the line looks like this. Okay, so this is the decision boundary. Just a little example here. Okay, so if this here, if x2 is greater than 0, okay, greater than 1, right? So if this was greater than 0. This is a positive class. Not positive, not x2, sorry. I'm going to rephrase. So if this term was greater than 0, and equal to, this is the positive class, and if it's less than 0, then it's the negative class. I just want to give you a little concrete example. Negative. Okay? And there we go. You can also have nonlinear boundaries here. So this is a linear boundary. Okay, so this is a decision boundary that's linear. You could also have nonlinear boundaries too. So you can have nonlinear decision boundaries exist. And we're going to see that in the next lab, in lab number 2, exist, right? You can also have something like this. Let's say you had, minus 1 plus. Let's say we had this instead, okay? In this case, theta 0 is 1, and then both of these, minus 1, I'm sorry. Okay, and then both of these guys, theta 1 and theta 2, are both 1. And then we're going to apply a nonlinear transformation. So x1 gets mapped, it just becomes squared. Okay, and in this case, you're going to get x1 squared plus x2 squared equals 1. Okay, so this actually maps to a circle. So it kind of looks like this. So 1. So Okay, so you have, a bunch of negative examples here, like that. Right, so these are negative. And then you have a bunch of positive examples out here, something like this, I guess. Okay, so if this is greater than 0, right, you make it a positive class, and then if it's less than 0, then it's negative. Just wanted to show you just a bit of perspective that you can have nonlinear distribution boundaries too, and we're going to actually talk about that in the next lab. Okay, cool. All right, let's see here. I'm going to skip the perceptron. We don't need to take a look. Actually, okay, I'll skip it this time. All right, multi-class, regression. Okay, let me just talk about multi-class for a couple of minutes, and we'll take a little bit of a break. All right? Okay, so okay, multi-class. We haven't really talked about multi-class yet because we've only talked about the case where there's binary between, true and false, 0 and 1, and so on. Okay? So far we have only talked about the binary case. Sorry, I can't write. Okay? So some problems have more than 2 classes. Okay? This is what's known as multi-class classification, right? Okay? There's several examples, right? For example, let's say you wanted to predict the weather, right? If you wanted to predict whether it's, raining or snowing, or if it's sunny, or if it's cold, right? So the weather belongs to a set of multiple classes or multiple groups, okay? So, sunny, rain, snow, cloudy, right? And then each of these take on a label. So let's say this is y is equal to 1, y is equal to 2, and then 3, and then 4, for example. It's not just 0, 1 anymore. You can make them up to as many as you want, okay? There's also, medical diagnosis. Instead of taking a look at tumors, you can take a look at, how sick the actual patient is. Whether if they're not ill, or if they just have a minor cold, or if they have a flu, or if they're really sick. Like there's different stages of sickness you can take a look at, not just sick or non-sick, right? So not ill, there's a cold, there's a flu, right? So you can group these into different classes. So this is 1, 2, and then 3, and so on. Okay, so there's different examples you can take a look at. And let me just show you a little bit of a diagram. Okay. This is taken from Andrew Ring from Stanford. I took it from his Coursera slides. Okay, so this is what we had before. Okay, so we had, let's just consider 2 features for now. X1 and X2, all right? And then binary classification is just to group it into 2 different groups. And, the best line of separation might be here, I guess, something like that. This is the negative class and this is the positive. Okay? And now with multi-class, there's a whole mishmash of points, and then each of them may belong to, instead of just one of 2 classes, one of, let's say 3 classes, for example. All right? So this is 3 classes here. Okay? So how do we perform multi-class classification? Okay? It's a technique which is called one versus all. You may have heard of it, you may have not, but it's okay. Okay, it's called one versus all. So the basics behind one versus all is you train multiple binary classifiers. So let's say we had 5 classes, for example. You're going to produce 5 different binary classifiers, where the first classifier, or the first set of parameters, you treat class 1 as positive, everything else is negative, and then you train a binary classifier. That's the first one. Then you take a look at class number 2. You treat all those as positive, the rest of them as negative examples. You find the parameters for that model. And then you keep repeating. You keep 1 as the positive class, the rest of them as negative classes, and you train based on that. And then you're going to have 5 different classifiers as a result. And what one versus all means is that you're going to take a new instance and you're going to put them through each of the classifiers and figure out which one has the highest probability that it belongs to one of those classes. And then you choose the class that has the highest probability. So that's what one versus all means. You take a look at one class at a time, compare them with all of the other ones for each classifier that you have, and then you choose the class that has the biggest probability that it belongs to that particular class. So that's what one versus all means. So it's very simple. You're just repeating the classification, you're repeating the training n times, where n is has however many classes as you have. All right? So, process. So just a couple more slides and we're going to finish up. Okay, so given that there are n classes in the training set, for each class k, going from 1 to all the way up to n, what you're going to do is you're going to take the training examples. I'm almost done here. Let's take a break. Take the training examples that have label k and make positive. Okay? And then the rest of the examples are negative. Okay? And then what you're going to do is you're going to train a binary classifier. So you're going to find the parameters where you assume that the training examples are positive for that label k and negative for everything else. So train a binary classifier with this labeling. And create a prediction model. Okay? For class K. Okay, in this case we got, okay, so we have hypothesis for class K is probability that the output class is K given the input n parameters. Okay, so to classify a new instance, choose the class that gives the highest probability. So what I mean specifically by this is you're going to take this input and put it through every classifier that you have that was trained in a specific way, and then take a look at each of the outputs and then choose the one that has the largest output. All right? So submit X to each model and choose the class with the largest output. Okay, so I'm going to show you a little picture just to make things clear, and then we'll take a break. So here. This is called one versus all. It's also called one versus rest too. So this is pictorially what the process looks like. So the class to choose is whatever the maximum gives you for that particular class. So the subscript k here is the classifier for that particular, for that particular class. So in this case, this is what happens for class number 1, right? You treat this is the positive, right? And then these are all negative. And then you might want to find a boundary that kind of looks like this, I guess. And then this is the second one, right? So this is positive. And then, something like that, I guess. And finally, this is positive, this is negative. and then something like that. Okay, so you have three different classifiers that assume that each one of those labels is positive, the rest is negative. You find the parameters, and then you choose the output that gives you the largest probability for a new instance. Okay, and that's how you do it for multi-class. So it's just a chain of different binary classes together, binary classifiers together, and then you choose the one with the largest output. Okay, so we'll take a break. We'll take a little bit of a break, and we'll come back and we'll talk about overfitting and regularization.